Welcome to the Deep Dive. This is your shortcut to being genuinely well-informed, packed with surprising facts, and just enough context to make it stick. Today, we're doing a deep dive into the critical world of non-destructive testing. Specifically, we'll be focusing on the principles and procedures from Magnetic Particle Testing Explained, our mission, to quickly get a handle on the core science, the applications, and the essential procedures needed to ensure material integrity without damaging the part.
And that last bit, without damage, that's the absolute key difference, isn't it? When engineers use NDT, they're really asking, is there something fundamentally wrong with this material structurally? It's quite different from, say, performance tests or proof tests. Those ask, does this thing work? And often those tests can push the part until it actually fails. Think hydrostatic testing, for example.
Okay, right. So let's unpack that a bit. Why is NDT so, everywhere now, across all sorts of major industries, aerospace, infrastructure? It seems like a massive industrial investment.
Oh, it is a huge investment. But the payoff is, frankly, human lives and better cost control in the long run. NDT is fundamentally about managing risk. By ensuring product integrity, making sure things are reliable, manufacturers avoid those catastrophic failures, prevent accidents, and maintain consistent quality.
And it feels like the pressure to perform these tests is only going up. I mean, designers are constantly pushing the limits, right? Lighter parts, smaller parts, sometimes swapping out steel for aluminum or magnesium.
That's exactly the challenge in modern design. When you make components lighter and smaller, they inevitably end up facing higher levels of fluctuating stress, what we call dynamic stress. And that kind of stress really speeds up fatigue and potential failure. So NDT becomes this essential tool, this risk management tool, to make sure those lighter, more stressed parts keep working safely throughout their intended life.
Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description. Okay, so now we get why NDT is so important. Let's get into the mechanics a bit. When we talk magnetic particle testing, or MPT, we're dealing with something called flux leakage. How do we actually see this invisible magnetic thing happening?
Well, the main distinction with MPT is that we use actual ferromagnetic particles. They are the indicating medium. While sometimes people use flux leakage testing for methods without particles, in MPT, it's the physical dust, the particles themselves, that are the star of the show.
Right. And before we dive deeper, we absolutely have to mention the basic requirement here. This whole process is strictly limited to certain types of metal, correct?
Precisely. The material absolutely has to be ferromagnetic. So we're talking things like iron, cobalt, nickel, even gadolinium. These are the materials whose internal atomic structure allows them to be strongly magnetized at that domain level. Otherwise, the test just plain won't work.
Okay, so walk us through the physics then. How does applying a magnetic field to, say, a solid chunk of steel actually show you an invisible crack just under the surface?
It all starts inside the material with what we call magnetic domains. In a piece of steel that hasn't been magnetized, these domains are like tiny little magnets pointing in all random directions. So overall, there's zero net magnetism. But when you apply an external magnetic field, those tiny domains snap into alignment. Now, if there's a discontinuity in there, like a crack or maybe a void or an inclusion, it basically acts like a tiny air gap.
And magnetic flux lines really hate air gaps.
They absolutely despise them. The path of least resistance for that magnetic flux is always through the metal itself. So when the flux lines hit that air gap, that crack, they're forced to detour. They have to exit the material, loop around the gap in the air, and re-enter on the other side.
And that interruption, that detour, is the key. Because when the flux lines pop out and go back in, that creates something we can actually detect.
Exactly. That interruption creates localized north and south poles right there on the surface, on either side of the discontinuity, the crack. And this flux leakage field it creates acts like a sort of microscopic magnet. It's strong enough to attract and hold on to those fine ferromagnetic particles we apply during the test.
And those particles just pile up along the edges of the crack, forming a visible line, an indication that outlines the flaw. So, does a denser line of particles mean a stronger leakage field?
That's generally correct, yes. The intensity of that leakage field and also its shape or curvature directly influences how many particles get attracted. And that determines how dense, how visible the final indication becomes.
Okay, now we know how the crack grabs the particles. But this whole thing only works if the magnetic field is set up correctly relative to the crack, doesn't it?
Yeah.
Let's talk alignment. What's the single most critical factor for successful MPT?
Orientation. It's everything. The magnetic flux must be induced at, ideally, right angles perpendicular to the main direction of the suspected discontinuity. That's crucial for the best detection. See, if the magnetic field lines happen to run parallel to the crack, they might just jump right over it inside the material without leaking out much, or at all. And if that
To see
happens...
nothing, even if the crack is there.
Exactly. You see absolutely nothing. A dangerous false negative. So the goal is always to make the magnetic field cut across the crack.
Cut the crack with the field. Okay. Speaking of setting up the field, let's talk power sources. If our main worry is finding a typical surface fatigue crack, what kind of current immediately comes to mind, and why?
For purely surface flaws, definitely alternating current, AC. Because of a phenomenon called the skin effect, it's some electromagnetic thing. AC fields get concentrated right near the surface of the conductor, so it's incredibly effective for finding those really fine hairline fatigue cracks right on the surface. But the downside is it offers very little benefit for flaws that are buried deeper inside the material.
Right, so if we do need that depth,
Mm-hmm.
maybe we're looking for a crack under some chrome plating or an issue deep inside a weld root, that's where direct current DC or its variations come into play.
That's exactly right. DC distributes the magnetic field much more uniformly across the entire cross-section of the part. That gives you significantly better depth penetration for finding those subsurface cracks. Although, one thing with straight DC is that it can sometimes cause the particles to settle too quickly, which might make very faint indications a little harder to spot.
Ah, okay. And that leads us nicely into the sort of hybrid option, half-wave rectified current, or HWDC. That seems like the most versatile choice, especially for field work.
HWDC is extremely effective, yeah, particularly when you pair it with dry magnetic particles. It's really good at detecting both surface and subsurface flaws. And the reason is the rectifier doesn't produce smooth DC. It creates these pulses of current. What's really interesting is that these pulses give the magnetic particles extra mobility. It's like they're getting jiggled around a little bit. This helps them migrate towards even quite weak leakage fields and build up an indication. It really aids formation and helps avoid, non-relevant clumps.
That makes perfect sense. A little vibration helps the dust settle exactly where it needs to. Okay, let's talk hardware. How do we actually generate these fields? What about the portable gear you often see out in the field?
Sure. We have a few main methods. For creating a circular magnetic field, we often use prods. These are basically two handheld electrodes connected to a mobile power unit that you touch onto the part's surface. They're quick, but they come with a significant risk. You have to use them really carefully to avoid arc burns.
An arc burn sounds bad, exactly like what it is, probably.
It is bad. An arc burn is basically a small spot of intense heat damage caused by poor electrical contact or sparking. And the moment it happens, you've just created a brand new, unacceptable flaw right there in the material. We often tell trainees, if you see a tiny little metal shaving sticking to the prod tip after testing, that can actually be a good sign the field was strong. But if you see a spark when you make or break contact, that's a bad day. That's damage.
Okay, good to know. Then you have those U-shaped devices. They seem really common for testing welds and things like that.
Ah, yes, the yoke. That's probably the most common portable device. Yokes use an internal coil and a laminated core to generate a longitudinal magnetic field in the area between the legs or poles. They're great for spot checks, especially on welds or parts with awkward shapes out in the field. And lastly, for hollow parts like tubes or pipes, there's the internal conductor method. You pass the current through a separate bar placed inside the hollow object. This induces a strong circular magnetic field on the inner surface, and it neatly avoids any risk of arc burns on the part itself.
We'd also like to recognize Skaggs Media, LLC, as the creative force behind today's podcast. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com. All right, moving on to the particles themselves, the stuff that actually shows us the flaws. We've got two main types, right? Dry powder versus the wet method. What makes you choose one over the other?
Yeah, the choice really boils down to the sensitivity you need and the kind of flaw you're looking for, plus the inspection conditions. The dry powder technique uses, larger particles. They can be up to about 180 micrometers in size. Because they're bigger and heavier, they're generally less sensitive to superfine surface cracks. However, they're often better for locating slightly larger subsurface discontinuities. So you see dry powder used a lot on large castings, forgings, welds, often out in the field, and usually paired with that pulsating HWDC current we talked about.
And the particles come in different colors too, right?
Yeah. Oh, yeah. Black, red, gray, blue, yellow, white. Depends on the surface color of the part you're inspecting, just to get good contrast.
Okay. And the wet method sounds like it's aimed at finding the really tiny stuff, maximum precision.
Absolutely. Wet method particles are microscopic, usually only 5 to 20 micrometers, tiny, and they're suspended in a liquid carrier, which could be a specialized oil or treated water. Because these particles are so incredibly fine and mobile in the liquid, the wet method is vastly superior for detecting extremely fine surface cracks, those tiny imperfections that the larger dry powder particles might just bridge over and miss completely.
But the real revolution, the thing that made inspection faster and maybe more reliable in many cases, was adding fluorescence, wasn't it?
Oh, absolutely. It's become the standard for a lot of high volume or critical inspection. Fluorescent magnetic particles, these have that special fluorescent coating. So when you look at them under UV radiation, what most people just call a black light, any indications where the particles gather just glow brilliantly.
They really pop.
They really do. And a little detail, the light these particles emit peaks around 525 nanometers. That wavelength is right in the green part of the visible spectrum, which is why you see that distinctive, super bright, almost unnatural green glow against the dark background. Our eyes are quite sensitive to that color.
That level of contrast, getting those faint green lines to stand out, sounds like it needs really specific viewing conditions. How tough is it to actually maintain the right lighting standards?
It requires real discipline and the right setup. Standards like ASTM-E 1444 are very specific. You need a minimum UVA light intensity hitting the surface, typically 1,000 microwatts per square centimeter, but just as critical to get that high contrast, and you can get contrast ratios of 200.1 or even higher. You have to keep the background visible light super low. The maximum allowed is usually only 20 lux or about 2-foot candles.
Wow, 20 lux, that's really dark.
It's practically pitch black. You need time for your eyes to adapt. It's definitely challenging to maintain, especially in some environments, but it's absolutely necessary if you want reliable detection of the finest flaws using the fluorescent method.
Okay, let's start to wrap things up by looking at the processes that ensure this testing is actually reliable. Standards, quality control, safety.
Yeah, reliability is everything, especially when you're talking about aerospace or power generation components. A truly reliable MPT process has to do two things perfectly. It has to find all the rejectable discontinuities, every single one. And, just as importantly, it has to yield no false calls. You don't want to be rejecting perfectly good parts because of misleading indications. That's where the human factor, the inspector's training and judgment in applying the standards becomes so critical.
And that ties straight into the need for strict training and certification for the inspectors themselves.
It absolutely does. In North America, ASNT's recommended practice, no. SNTTC1A is the cornerstone document providing those guidelines. For instance, to become a Level 1 or Level 2 certified MPT inspector, candidates have to pass pretty tough written exams. There's usually a general exam covering the principles, maybe 40 questions. And a specific exam on the procedures, they'll actually use perhaps 20 questions. They typically need a composite score of 80% or higher, and crucially, they can't get below 70% on any single exam.
And they have to recertify periodically, too.
Yep. Recertification is required to ensure they stay current, usually every few years, with the maximum interval typically being 5 years.
Now, we mentioned earlier that magnetic field physics can get complicated, especially when the part's shape isn't simple. Fields varying because of geometry, maybe even canceling out at certain points. Given this complexity, how do inspectors make sure their field strength is actually adequate for the job?
That's a great point, because just calculating the required current doesn't always work perfectly for complex shapes, practical experience, and, well, rules of thumb have always played a role, but you can't rely solely on that for critical work. That's why we use objective reference standards. Things like the tool steel ring standard. It's a standardized ring with known artificial subsurface defects. By testing the ring, you can verify that your whole system, the amperage setting on your machine, the effectiveness of your particles, your lighting is performing correctly before you start testing actual parts. It's a crucial process control check.
Okay, makes sense. Finally, let's quickly touch on safety. What are the main hazards inspectors need to be aware of? Starting with chemical hazards from the materials used.
Right. The expendable materials, things like the petroleum-based carriers for wet particles, cleaning solvents, the particle pigments themselves, they're generally not acutely dangerous if handled properly. but proper handling is key. Inspectors absolutely need to read and understand the material safety data sheets, the MSDS, for everything they use. For example, some older solvent carriers might have low flash points, which means a serious fire hazard. Plus, the vapors can be irritating or harmful to breathe, so good ventilation is essential.
And what about the radiation aspect? We talked a lot about using UV blacklights.
Yes, radiation safety is important too. The UV light needed for fluorescent inspection is specifically UVA, which is in the range of about 320 to 400 nanometers, typically peaking around 365 millimeter. This range is considered relatively low risk for short exposures. However, inspectors must be careful because black light lamps can sometimes emit small amounts of more dangerous wavelengths if they're damaged or not properly filtered, specifically UVB and UVC. UVB can cause serious skin burns like a bad sunburn and eye conditions like welder's flash or snow blindness. UVC is even more dangerous and can also generate ozone gas.
So eye protection is a must.
Absolutely non-negotiable. Proper UV-blocking eye protection must be worn during fluorescent inspections to prevent potential long-term damage to the eyes, particularly the retina. Safety glasses designed for UV work are essential.
Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsll3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing. Okay, so to quickly summarize this deep dive, magnetic particle testing is basically using magnetic flux leakage, made visible by tiny particles. Getting it right demands really careful control over the type of current AC for the surface, DC or HWDC, for deeper flaws, and critically, making sure that magnetic field is oriented perpendicular to any suspected cracks.
And maybe here's a final thought to leave you with. After the inspection is done, the very last step is often demagnetization of the part. Now, you might think that's just to stop metal chips from sticking to it during later machining. And that's true, but often there's a much more critical reason. If you leave a significant residual magnetic field in certain types of components, it can cause serious problems later. It can lead to arc blow, where the magnetic field deflects the arc during subsequent welding operations, making for a bad weld. Or even worse, in precision-moving parts like engine crankshafts or bearings, a residual field can attract wear particles or interfere with magnetic sensors, potentially leading to premature or even catastrophic failure down the road. So that leftover magnetism can completely undermine quality and safety, even if the MPT test itself found no flaws.
Wow, that really drives home how the entire magnetic state of the part matters, not just the flaws it might contain. A level of detail and precision in NDT really is crucial for ensuring the things we rely on every single day don't fail us unexpectedly. So what does this all mean for the next component you see? Keep observing, keep learning.